Area under the curve may be the most famous, or may I call it infamous, statement on integration. Infamous because for most it is a point of disconnect, given that integration learnt via limit and continuity leaves little room for visualizing area under the curve, and which area and how it is computed. However, exploring integration as the area under the curve of the integrand functions is a world of delight and insights. It is truly simple too. Recall, we have already explored how area under the curve of a speed-time graph gives us the distance traveled over a period. We went through the mathematics of the same. It was like the physical evidence of what really is integration. Thus, in this reel, we explore the general nature of the antiderivative of the function f(x) equal to x square. That is, we would explore the integration of x square, a parent function, by geometrically computing the area under its curve. And we would seek the parent function of its integral, something that is intuitively achievable. We will not use the familiar methods of calculus to get the function that is the integration of x square, for that would be of little value, conceptually speaking. We would follow the first principle, make the curve of the function x square, decide on the interval or part of the curve for which we would compute the area under it, and lastly, plot the curve of the function that represents the integration of x square. However, this begs one question. How is the area under the curve of the integrand function? X square, in this case, is connected to the curve of the function that is the integral of x square, or the outcome of the integration. We are now at the cusp of the most important and interesting discovery about the essence of integration, about visualizing what integration is all about. I must admit, it was an epiphanous moment for me when I finally connected the famous area under the curve of the integrand to the curve of the integral. The area under the curve of an integrand at a point is the value of its integral function at that point. It is the specific value of the integration of the function. That is, the values of the integral of x square are the values of the area under the curve of x square. Thus, the curve of an integral function is plotted with the y-axis being area under integrand curve for the various points of the independent variable x. That is, the integral of x square is plotted with the values of the area under the curve of the function x square being on the y-axis, and the corresponding values of variable x on the x-axis of the integral curve. That way, the coordinate points on the graph of the integral of a function are x-axis values and the corresponding area under the curve of the integrand. That is, the integral of x square will have the coordinate points x and the area under the curve x square. We will now visualize how we plot the graph, the curve, of the integral of a function. That is how we get the coordinate points of the curve of the integral. We will use the graph of a straight line to illustrate. It is the simplest illustration. This is the graph for f(x) equal to x. At x equal to 0, the area under the line is 0. Thus, one coordinate point of the integral function would be 0, 0. This is the area under it at point x equal to 1. And if the area is 0.5 up to x equal to 1, then the next coordinate point of the integral of the linear function would be 1 on the x-axis and 0.5 on the y-axis. This is the area under it at point x equal to 2. If the area is 2, then another coordinate point of the integral function would be 2 on the x-axis and 2 on the y-axis. And this is the area under it at x equal to 3. If the area is 4.5, then another coordinate point of the integral function would be 3 on the x-axis and 4.5 on the y-axis. We can now plot 0, 0, 1, 0.5, 2, 2, 3, 4.5 on a coordinate plane, and the graph will be that of the integral for f(x) equal to x. Hopefully, the computation of the coordinates of the integrals is well illustrated, and we can get on with plotting the integral of x square. This is the curve of fx equal to x squared. And we use the x and y coordinates as shown in the table to plot the curve of x squared. We will find the area under its curve at various points. The area would be measured for the triangles under the curve. In the integration lesson, we have studied why and what is the area under the curve. It may not be repeated here. The area would be some approximation, as the one of the sides of the triangles is the curve itself. But mostly the computation is not affected for the lower values on the x-coordinate. Let us take the plunge and compute the area under the curve at 5 points on the x-axis. The first being the origin, the area under the curve at origin being 0. This is the area under the curve at x equal to half. Thus, the area is between 0 to half on the x-axis. This is the area under the curve at x equal to 1. Thus, the area is between 0 to 1 on the x-axis. This is the area under the curve at x equal to 1.5. Thus, the area is between 0 to 1.5 on the x-axis. This is the area under the curve at x equal to 2. Thus, the area is between 0 to 2 on the x-axis. If we plot the coordinates, we get this curve. The curve of the family of x cubed function. Indeed, the integral of x squared belongs to the family of the cubic function. Let us just say that the integral of the quadratic functions is a cubic function. We simply use basic geometry to find the integrals of functions. Of course, this lesson is only meant to help visualize the way integral curves are created, to consolidate the entire conceptual nuances and the expanse of finding the integral of functions. Solving is anyway much simpler. It is almost wholly algebraic and trigonometric competencies. Hopefully, imagining the process of integration is not hard. We can use calculus computation or precise geometric computation to see that the exact integral of x squared is x cubed by 3. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.